speakers are from a company called Eltan. This is a design company. They design hardware and firmware, and they built a really small but really awesome PC, and they're going to talk about it. And so give it a round of applause.
Thank you. Good afternoon. I hope everybody's still awake after lunch, and otherwise I have to shout awake. But meet ORWL. ORWL is a special project we like to share the design and development with you. It's a system based on Skylake. On top of that, a coreboot with a TianoCore payload, UEFI TianoCore payload. Open hardware, open software. So, yeah, let's present a couple of slides to you. It doesn't go well. This is no. This was it. Okay. Okay. ORWL comes with it's a complete PC. Yeah, a device like this. This is a real one, and this is a development unit with two key fobs. We are from Eltan. My name is Gerard Duynisveld, and in Vervoorn we will split the presentation. A little bit on Eltan. We are an independent engineering company. Some advertisement. We assist companies deploying PC and communication technology. We are a Phoenix authorized developer. We picked up coreboot since 2013, and we see a great market for some great future for coreboot in some markets. At this moment, not everything yet. We are also an Intel fellow traveler. We provide highly specialized engineering services, especially around firmware, BIOS, Phoenix or coreboot. We are an Intel and AMD source code partner, so we have access to the source codes of both companies. Further, embedded controllers quite often in your design, quite some knowledge on that, hardware design system, and we also have some custom development tools just to assist our customers with faster developing PC hardware and firmware. We are also still a Windows embedded partner. Back to the slideshow. Nearly. Yeah, okay. It has received a number of awards. I'm not going to show them all, but the CES, Popular Science, and last week I think it was, last week Popular Science, last week it was Wired. Protecting data is critical. Yeah? It's all sorts of cyber attacks. Data stored or valuable and need ultimate security, and really protecting something starts at the hardware, at the real bottom level. It was a new concept, so basically you have to protect from attacks like walk-in, injection of USB keys in your device, or sneak in and remote access IP spooking, break-in, opening the device, or damage the equipment and altering temperature, drilling holes. And you saw with these shields, it's made it impossible. The presentation from Philip that he was searching with heat the different patterns in the ICs, that's made it impossible with this shield. It's an open source project, open hardware, open firmware. The hardware is still not available, but they will open it up, they said, after some 3,000 devices, so they want to have a head start of making production possible and getting return on investment. As you saw, you need a fob to open when you start a device that's within 4 centimeters, and then you can walk away for around 10 meters. If you go further, it will automatically lock down. If you move it like this, there is also a videoscope in it, it will also lock down. If you try to open it, the data will be destroyed on the device. So, yeah, it's a new device, a new category of for security information, and it is a complete PC. Diagrams. Yeah, it's built on top of the Intel Skylake. There's a secure controller controlling the die mesh, but also with the key fob. And now it's getting technical, so Wim will take over.
Okay, as you can see, we have the secure controller on this board. That's really the heart of the security system. And that's a Maxim 32550 chip. And the key fob is an NFC implementation combined with Bluetooth low energy. And basically, it's a Core M, and it has everything enabled. You can run basically any OS on this system. And here you get a little bit about the ranges where the security can operate. So you have the close ranges, the authentication. Then here it's still 10 meters, and in reality it's extended to 30 meters. The range that you can have with the keys, but you can control that between 5 and 30 meters, what the range will be. So this is what the key looks like. In the secure controller there is an NFC reader, an NFC reader from NXP. It's just a standard smart card solution basically, which also communicates with the Bluetooth beacon, so it knows this beacon belongs to this system, so it's hard to fool with that as well. And what you can see on the right, that all of the system, so the secure controller and the Skylake subsystems, all of them are within this secure mesh to protect it. I will go a little bit over the architecture of the system. Look at the hardware, which is based basically on a Skylake notebook reference design, so it's a Skylake Y. The firmware, we have a coreboot with the TianoCore payload, and you can run all operating systems. So this is how it looks mechanically. Both sides of the board you have this honeycomb structure with connections to the main board, which in fact also connects to this secure controller. And on top also you have an OLED module for the user interface of the authentication. This is a kind of exploded view. We didn't have all the components separately, so that's why we have a picture like that. You get an impression. The outside is usually a glass hardened glass outside. This is how they look from the top and the bottom. And this is the inside of the mesh and the board itself. So it's fairly dense. It's fairly dense design. And the mesh itself is made of special kind of plastic. So if you try to manipulate it will easily break. If you do that, you get little cracks in it, and the system will detect this. And that's been also verified and validated by an agency who looks at that kind of security solutions. Yeah, so the key fob is about an ST device, card emulation mode. So that's pretty standard, and it's a pretty nice key. It's basically a smart card with Bluetooth added. The ORWL system, yeah, you have the secure controller, which is running 3 hardware with several extensions to implement all these security protocols. And that's a part that's been made by DesignShift, which is the original vendor of this system. So this is a little bit more in detail. So you can see that it's basically, yeah, like a typical notebook, also with the USB 3C implementations in it with multiplexers. So you can have power delivery on both boards, so you can connect your power supply to the USB-C connector. You have 2 of those on the system. And micro HDMI. And what you can also see is that you have, besides the standard solution, you have additional switches which are controlled by the microcontroller. So if the microcontroller detects you're out of range, it can remove the USB signals from the bus. So there's no way that you can do something on the USB bus after that anymore. And also the screen will be can be blanked by doing that. And that can be controlled by the secure MCU. It can be forced. Also the secure MCU can control the power of the system. So it will only turn on the power basically after it's verified the system is in a good state. So this is basically the center of the security solution. What I told NFC, Bluetooth for proximity protection, motion sensor, and it constantly monitors the mesh integrity. Also when the system itself, that doesn't matter, it's got a battery inside, and it will monitor at very low power if you try to do something bad with the mesh. So it will be very hard to manipulate that. It also stores the main product keys that are in use in the system. And they can very quickly be erased using this secure control. Basically the keys that it preserves are all encrypted with one master key that will be instantly deleted when it detects tampering. And it also contains a real-time clock, and that's the real-time clock that will be used by the system as well. So the system will always synchronize with the real-time clock in this secure controller, so that can be monitored as well to prevent manipulation of that. And before the system can start, it will verify flash integrity, or at least the first part of it, so we can start a secure boot chain independent of the management engine. And we have control over, as we know for sure, that the boot block and the first verification stages, and also the hashes that we create from various blocks are correct. And it will normally, if you get out of range, it will request the system to sleep or to perform the action that you want. You can configure that. It can force the system off. If the system doesn't react in the way that it should in time, then the system will be forced off. So also when there is a problem with the OS or somebody somehow tries to prevent the normal flow, that will be overridden. It uses the OLED for the UI. The UI is pretty limited, but still to make it a clear experience for the user, because that was one of the goals. It should be have high security, but it shouldn't be a difficult system to use. So that's why this UI is added. And for the Skylake itself, it's Skylake Y. It's based on node preference design. And, we have the USB-C ports, micro HDMI, also a Bluetooth and Wi-Fi controller on the board, which are independent from the Bluetooth which is used by the Maxim chip. We use self-encrypting SSD, and it's got 8 GB of memory. So if you look at the firmware, yeah, I think that I'm probably one of the few people here who dares to put the UEFI logo in the presentation, but I still do it. The requirements were as much as possible should be open source, but it should still be able to run stock distribution of Ubuntu, Linux, use a USB stick to install, it should work. Also CubeOS and Windows 10. And that should all be possible using the same firmware in the system. So that's why we decided to use, and also there should be a pre-boot UI for configuring the secure controller. Because of that we used coreboot combined with Tiano payload. And that's about it. So this is basically the architecture that we're using. It's coreboot as the bottom layer to configure all of the hardware. Basically the biface of the TianoCore system, and then we have a stripped down TianoCore with sufficient capabilities to boot the system. Of course, it's a pure UEFI system. There's no legacy support in it, no C-BIOS, or it could be done, but it's not there to make a boot like that. And we have an FSP inside, but that's standard for any Intel system, I think. And this gives a little bit of an overview of what happens when you boot the system. You first you insert power, so then the secure controller will wake from its sleeping state. And if the user then presses the power button, he will be asked to authenticate. And if that succeeds, or we will first check if the BIOS is tempered or not, and the system is tempered or not. But if there is a valid key and a known BIOS, it will boot the computer, and the proximity protection and the motion protection will be active after that, and it will monitor the proximity of the key and the state of the system. And also if the system is tempered, it will still be booted, but it can only boot one boot path, so just to show the user, okay, your system is tempered, and that was the reason, that's the time it happened. After it will be there for 30 seconds, and then it just will shut down. It's just as a convenience for the user that it's not a dead system or something. So what did we add? We added specific support both in the coreboot part and in the TianoCore part. We also addressed requirements that had to do with production of the system and the entire flow from the PCB line until your customer. So that's why we implemented various system states. So in some states the system will boot unprotected, so there will not be no secure booting authentication. So in the factory, tools can be used, unsigned tools can be used to manipulate the system. And that's a decision of the customer of what they wanted to do in that stage. And also we expect certain features in production stage. It should always be booting from USB, while it's a user state. We don't want it ever to boot from a USB stick. So there are the differences that are all addressed in this area. And also we can't use every feature of the secure controller until some keys have been paired with it. Otherwise you can't really know what kind of user is connected to the system, and you can't use the SATA disk yet. So this is more or less providing these system states. So it's all the way from production test to out-of-box mode, so that the user selects his own PIN code to access the system. So to access, it's not only the key, but it's also a PIN code that you have to enter. Yeah, you can only do that the first time. So what I told, the USB booting, that's kind of a special thing. We don't want it to be boot from USB normally. So what can be done is the user can get into setup and can request one USB boot that can be used to install the OS or whatever task you need to do, and it can only be used once. And there was also a request to have the UEFI shell in this system accessible to the user. So what we also did is to make sure that the block devices will not be loaded on the USB devices. So even from the UEFI shell, you can't go to the bootloaders on the disk. Otherwise, the feature would be gone, and you can still boot from any USB stick to any software. For flash update, to have that open, we used Flash-ROM. But of course, as different operating systems can be used on the system, and we don't want a lot of hassle for the customers, what we did is create a small Linux distribution, pack that into an EFI file, so it can just start this distribution with Flash-ROM inside and the actual flash update inside as well, as a command from shell, or once the system is out of production mode, it can only do it from a specific location, from the EFI system partition, a specific location, and after you enabled flash update. So you need to do that on purpose. It will reboot afterwards and will boot straight to the flash update mechanism. And if you don't do that, the complete flash will be locked and you can't access it. So we also have a verified boot. So the initial stages are verified by the maximum chip, and afterwards we verify hashes of the RAM, ROM stages, the FSP, the payload, and the other stuff. And once the control is transferred to the payload, we use the UEFI mechanism for the protection. And also the boot select sequence in that area, and the way we deal with secure boot verification has been modified to fill the needs of this specific project. The tempo protection, that's already told that it will be detected completely by by the Maxim chip, and when it detects the tampering, it will report a different system state to the system if I request which system state the system is in, and then the coreboot and the payload will take different decisions based on that state. So the only thing you can do is then see what happened and why the system was tampered. And how at what time. We use self-encrypting SSD, so we rely on that. There's nothing special has been done with it. The data used to unlock it is stored only in the Maxim chip. And so we use that to unlock, and even when we resume from S3, we get information to unlock it from the secure controller, so we don't preserve it on when we are booting as we would normally do. And that also allows that if the system was tampered between operation and S3, that it doesn't resume anyhow. The support is coreboot needs to interact with the secure controller very early, also to support the S3. And to recover the SSD, which has as a user and a password, and user and a master mode, you can erase the disk to recover it, at least the physical disk. The data is gone off. Key is thrown away as well. And the user also has an option in the setup to request an erase. So then the keys will be thrown away, the disk will be erased, and you have a clean system for next install, or if you transfer the system to another user, then it's a quick way to make sure that you can do that. And what we did find out is that normally you can when you use the UEFI system, you can reboot into setup to get to that menu. If you do that from Windows, you can't use this feature because it locks the disk. So you can only do that if you boot into setup right away. That can be done as well. There is also the user can also disable the Wi-Fi, and if that's done, we disable the root port in coreboot to make sure it's not possible to later access the Wi-Fi module and enable it again. So for the proximity and motion detection, that's partly a setup feature, so we have to communicate those settings to this secure controller to make sure it knows what it should do. And once it detects that, we will first try with standard ASL code to clear the screen, or to enter S3 or shut down the system in the regular way. But there is a timeout on that, and then if it doesn't succeed in time, then it will be turned off to be completely sure. And things like the disabling of the USB ports, that's a hardware item completely. Also what we've done is make sure when the system starts, we have time get the time from the secure controller. Basically the secure controller can monitor that and can make sure that you don't try to do any strange things with it. And during runtime, the runtime UEFI API will communicate with the secure controller as well, but in a lot of cases that's not used, and OS is directly manipulate the RTC. So in that case we also synchronize the RTC inside the Maxim with the RTC from the system. but the micro, the Maxim can reject that if it notices things that it doesn't allow. The user authentication is done with using a key fob and without entering the PIN. That's something that's up to the user. And it happens when you switch on the system, but also when you do things like entering setup, you need to authenticate as well. You can't simply go to setup and change all these sensitive things. And depending on what you change, you either can do it with just touching the key fob, or you have to enter a PIN code. And sometimes you have to do that twice before you erase the disk. You get a couple of requests to see if you're really sure about that. As a coreboot implementation, it's basically just another Skylake system. Even though it's a Skylake wire, if you look at it, the standard support from FSP is mainly from the IOTG group, and Skylake Y is not an embedded part. So some differences will apply, and we ran into some issues, and also we had to make sure we can flexibly decide between Skylake Y and Skylake H with GPIO mappings, PCI mappings, USB mappings, that kind of things which are different. And also to make the audio support work, we had to add firm tables for the HDMI audio support. And what we also run into, because we have different size BIOS area in the ROM than what Intel usually expects with the FSP. So when the cache was set up, the MTRRs expect to be only one MTRR, so 4 megabyte or 2 megabyte to set up. We had a BIOS area of 6, and that's where it screwed up and only put a 4 meg area, so the FSP wasn't cached. And we had very strange memory training results. So that took a while before you finally found out what the issue was. It's not that obvious. In order to be able to secure the SSD and to communicate with the disk early in coreboot, we partially ported the HCI driver from the payload to coreboot to be able to issue the commands we needed for this purpose. We also have the communication with this secure controller, and it's done over using a serial port still. Okay. So we have to do that in SNM and in RAM stage. And also the system will synchronize the system state in various places. So in a lot of places, before it takes an action, it will first check, okay, which state am I in, am I allowed to do it, because basically the state of the system can change any time. So we can't say at the beginning of the boot, okay, we're in that state and we stay there. So you use that. And what we also see as the secure controller is an always active element on this board, while the system is not. There are some issues to really take care about with leakage of power from one subsystem to the other, which can also cause very nasty issues if you try to power the SOC from secure microcontroller. We also had to tune the power supplies because the power budget of the system isn't sufficient to really provide the power that's normally specified by the VRAM, and to keep it down we can tune that. We supported cubes, we had to change some things. There's cubes, for instance. If he sees a coreboot as the BIOS vendor, it will say, okay, you run CBIOS, and so the install will completely fail. So we report now something like Eltan, TianoCore payload as well as vendor. And we updated the BDS ending because we noticed that the distribution has a CD partition and a hard disk partition. And if you start from the CD partition, Xen won't chain load. And if you do the other one, it will also. I would change the order from the normal way. And with Ubuntu, we noticed that they don't set the beat date to a valid value. It's not used, but okay. So we ignore that now. Operating system, so you can have it with Windows 10, Ubuntu or cubes installed. For Windows and Ubuntu, you can just take the standard medium, have secure boot installed and enabled, and it works. For cubes, it's a different story because they don't sign their EFI images and don't want to do that. So if you use standard distribution of cubes, you will be required to either disable secure boot or sign those EFI binaries yourself. So that's about it. So the time for some Q&A.
Wow, what a master project.
Hello, how does the security mesh work? Say I want to open the device, can I open it in some way?
No.
Can I replace the mesh if I break it?
No. If you do that, it needs to be returned to DesignShift to restore it. You can't do that yourself.
Do you actually have a battery on that board?
Yes.
So what's the scenario if battery drains? I buy that and I want to operate that for 10 years now, and no battery will hold that long, so
basically, I think it's in the manual that the last half a year without connecting it to power, so every half a year you need to do that. I think that's about the scenario, because
You have to use it, isn't it?
Okay.
You have to. Every day.
Yeah.
Hi there. So yes, excellent engineering. I have several, like a large number of security concerns, but I think there are too many to actually ask online. So maybe we'll talk after. How about the open hardware part? So you said this is open hardware, but then you said it is actually not yet open hardware. It will be sometime in the future. Because they want to sell a number of devices. That's understandable, I guess. But more importantly, what design tools were used to create these designs that will be published? Are those also open source, so that the data format is actually open, or is it done in proprietary tools which are significantly less useful to the community?
As far as I know, the schematic has been made in ORCAD. So it's not a free tool by far, but
The message of DesignShift is it's free open hardware, open software. And they, on questions from the public some time ago, they said, okay, we first want to have 3,000 units sold before we make it open. Yeah, to make some market momentum. And basically, they feel confident. They say we make great hardware, great software. Anybody may copy it, but if Quanta is the manufacturer of this, it's hard to beat them in production cost. So we can take up competition on an equivalent type of unit.
it's ORCAD.
I come back with the security concerns. So how do you want to protect the NFC and the Bluetooth Low Energy against range extension activities?
I I don't know that part of the project. We've done the coreboot and the Tiano payload part. So this part, let's say the secure microcontroller part, that was done by DesignShift themselves. So I don't really know.
Yeah, thank you.
My question is somehow related, but maybe it's still not. Is the key, which is the asymmetric key, is it generated in the hardware key on when the user has it in his hands, or is it created at factory?
As far as I know, it's created at the factory.
Created at the factory and they don't have copies. So you are the only one with the copies. If you lose them, you lose the data.
Okay, any more questions?
All right, I have some questions. The tech supports, are they used for power as well, or are they only used for? So, all right, how do you prevent a brownout of the device if, say, you have a high load of a machine?
Yeah, there is a controller also monitoring the power consumption. So it will be shut off if that seems to happen.
Yeah, sure, it's standards.
We use the PD protocols as well.
All right. And so in order to run cubes, I think you need the DMAR tables. Did you implement creating those, or the virtualization part?
Yeah, that was also created.
I wrote a whole this story. The secure controller, were you involved in the firmware that's running on that?
We're not involved in the firmware in that, so just with the API that we use to communicate with it in the functionality.
Do you know if that will be open sourced?
I'm not sure about that. I know it's based on FreeRTOS, and if it's open sourced, I know that significant part of it, or part of it at least, won't be, because it's proprietary for Maxim. The bootloader part of this controller, but that definitely won't be. But the other software might be. I don't know. You should ask DesignShift for that, what they do.
Right, so, and I just checked out the webpage. So there's the prosumer version that has the DesignShift keys, and then there's like the enterprise and the government version that allows you to put your own keys on there. Is there a way for, like, if I buy a device as a private person, to put my own keys in there, or is that?
You can update them, but the difference is that well, by default, if you buy the normal version, you will have the DesignShift OEM keys, and you will have those standard Microsoft and third-party keys installed in it. And yeah, if you have a Pro version, you can have your own keys in your own configuration.
Cool, thank you.
Okay, we have time for one more question.
The mesh that's built around the PCB, does that interfere with the wireless signals? I mean, you have all those senders and receivers, and then you have that mesh. Isn't that a Faraday cage?
No, they are outside of this.
The antennas are outside.
Yeah.
So there's a cable that's going over the mesh.
Yeah, they are going to mesh. Yeah.
Okay, that's it. Thank you. Your round of applause.